Welcome to the 7th class about direct policy search and reinforcement learning. Here we will consider the combination of evolution and deep reinforcement learning in the case where evolution is used to optimize actions. So in the previous lesson we have seen algorithms which evolve policies together with using reinforcement learning, and the idea of this lesson is that policy parameters and actions are vectors of numbers which can be optimized, and the point is that actions are smaller vectors than policies, thus they are much easier to optimize. So here we will consider algorithms which optimize actions within the reinforcement learning loop. Here you have a list of the systems that we will consider, and again this table is taken from this paper. On the previous slide, I justified optimizing actions from the perspective of moving from policies to actions when combining evolution and reinforcement learning. Now I will justify it from a second perspective, the perspective of moving from discrete to continuous actions in reinforcement learning. This perspective is already present in my playlist about policy search, but with a different focus. Let's start with DQ network or DQN. In DQN, you have a set of discrete actions, and the agent needs to look for the maximum over these actions at two places. First, to update the Q network, here you need the maximum over actions of the Q value of these actions at the next state. And here, to decide what to do in the world, you need to take the argmax over the actions of the Q values in the current state. The point is that you can do this when you have discrete actions with just one neuron per action, but you cannot use one neuron per action when you move to continuous actions. In the continuous action case, you have two things that become too hard. The last two previous things. First, selecting action by finding the argmax over the actions. That becomes an optimization problem. And then computing this max also becomes a computation problem. So there are three solutions to that problem. The first class of solution consists in changing the Q network so that it becomes a quadratic function where it's easy to find a maximum. So if you have something convex, you can use a Newton method or those kinds of things. That's the idea of the NAF algorithm. But this algorithm does not work well because in most cases the Q function cannot be well approximated with a quadratic function. The second idea is the idea of the DDPG algorithm. It is to train a side estimator of the best action, which is the actor. The idea is that the actor tries to provide the best action in any state. So it's a good approximator of the best action for optimizing the Q values and selecting this action here. The third solution is the one that is of interest to that particular video. It consists of, instead of trying to find the best action over all possible actions, just sample a set of actions and take the best over these samples. But rather than doing this naively, we will use an evolutionary method to find a best action over a sample after a few generations of an optimization procedure. So here we focus on the third class of solution. Before going into the corresponding algorithms and QT-opt in particular, I need to explain the notation for the use of the cross-entropy algorithm to optimize over actions. In the cross-entropy method, you start with a population of candidates. Here these candidates are actions, so I note them AI. Then I need to evaluate them with some function f, and then I will select the best actions given the evaluations. From the selected actions, I compute a covariance matrix, and from that covariance matrix, I will sample a new population of actions AI. And I can perform this loop several times until I'm satisfied. And when I'm satisfied, I just output the best action that I have found, which is the output of my algorithm. So the algorithm is parameterized by several things. First, the size of the action set. Second, the function that we use to evaluate the actions. Third, the number of loops. And finally, the number of samples that I select to compute my new covariance matrix. So in the next slide, I will summarize this whole algorithm with just this notation. I will use my best action is the result of applying the cross-entropy method over this evaluation function for this number of loops. So let's start with QT-opt. As I said, QT-opt is similar to DDPG. Actually, it has a replay buffer like DDPG. It has a critic so a Q network, and it has several other components because it can be trained with offline data and it trains several workers. But the important point for us is that instead of having an actor, it uses the cross-entropy method to provide the policy. So in more details, to update the critique, we use this application of the cross-entropy methods. So here the function that we want to optimize is the Q value of the actions at the next state, and we will just perform 2 loops. So we have an initial population of 64 random actions. We compare the Q values of these actions at the next state. We select a few of them. We obtain a covariance matrix that provides a new population of 64 new actions that we evaluate again, and then we take the best over these 64 actions to perform that update with the action we have selected. And for the policy, again, we take 64 random actions, we perform 2 loops of the cross-entropy method, and we take the best action. What I did not say when presenting the algorithm is that to compute the covariance matrix, we take just the 6 best individuals over the first iteration of the process. And the actions are complicated vectors with a feature vector with 5 dimensions plus 3 Boolean functions. So this algorithm was quite successful. The corresponding paper was one of the first to apply vision-based robotic manipulation, which is becoming at the moment a very hot topic. And it's interesting to see that they do so combining evolutionary methods and reinforcement learning methods. Now let's move to a second algorithm, which is cross-entropy guided policies, or CGP. CGP starts from the point that the main problem with QT-opt is that action inference is too slow. Actually, you need to sample these 64 actions to evaluate them, to perform an iteration of the cross-entropy method, and to evaluate 64 actions again. Okay, so that's very long, and that's too long to be applied on a working robot, which usually works at 20 Hz or something similar. So what they propose in CGP is to put a policy back, and instead of selecting the action with the cross-entropy method, you train your policy either using behavioral cloning from the actions that the cross-entropy method would propose, or using a gradient over the Q function as is done in DDPG. And if you use the gradient method, what you obtain is very similar to DDPG. The only difference is that to update your critique, instead of using your actor, you use the cross-entropy method. And what they show is that in practice, this algorithm is much better than DDPG on several continuous action benchmarks. It is somewhat similar to TD3. One drawback of the paper is that their algorithm is not compared to QT-opt, so it's not clear whether it outperforms QT-opt on those benchmarks. And also the gain with respect to TD3 is not spectacular. But their main point is that here the mean inference time does not grow with their method, whereas when you use the cross-entropy method with 2 loops, you need 6 seconds, and with 4 loops, you need 10 seconds, which is much too long to be applied on a robot. A third algorithm from the same family is GRAC. GRAC introduces several additional ideas with respect to CGP. First, instead of starting from random actions as in CGP, if you have a policy, you can sample actions from that policy, which is a better initialization. So here, instead of starting from random actions, they use the action that the policy would provide at the next state for that update and at the current state for selecting the action. This is something you also find in a more recent algorithm, which is called TD-MPC, and which is quite important in current research to train robots end-to-end. A second idea is to update the critique only if the Q value of the obtained action from the CM process is better than the one proposed by the policy. Actually, when the policy gets close to optimal, the cross-entropy method is mostly adding noise, so it's a good idea to keep the current best action that the policy proposes. In terms of performance, you can see with the slides that GRAC, which corresponds to the orange curve, outperforms many standard reinforcement learning algorithms and even EAS-RL. But one point is that they do not compare their performance to QT-opt, CGP, or other similar algorithms. I did not mention that they had a population size bigger than in QT-opt, and that they just keep the 5 best instead of the 6 best in QT-opt. And also they perform 2 iterations of the cross-entropy method. Also in the GRAC paper, they have several other contributions. One is the one that I have just presented to you, self-guided policy improvement with evolution strategies. The other one are that they use regularization in temporal difference learning, which is very interesting but out of scope. And they also take a max-min double Q learning, which is also very interesting but out of the scope of this presentation. And finally, they show that the various components of GRAC complement each other. So when you take the full GRAC, you always have better performance than when you remove some of the elements. Actually, that's not the case in Walker 2D and Hopper, but that's true in general. Finally, let's have a quick look at EAS-RL. EAS-RL uses particle swarm optimization rather than the cross-entropy method. That's a different process, which is a sort of cross-entropy method with some inertia and some acceleration capabilities. I won't go into the details. The evolutionary actions are used for behavioral cloning, so it means that the sampled actions are used to train the policy. And as in GRAC, they only update the Q values if the action that you obtain with particle swarm optimization is better than the one proposed by the policy. They call that Q filtering. But the difference with respect to GRAC is that if it's not the case, instead of doing nothing, they use standard gradient descent as in any reinforcement learning algorithm, which is better than doing nothing. And in terms of results, a big limitation is that they do not say how many seeds they use to obtain their curve. And you can see that many times the difference with respect to existing algorithm does not seem to be significant. So I find these curves mostly interesting because they allow us to compare other reinforcement learning or combination algorithms. Finally, they also have a setup where they introduce some delay in the environment, which is quite interesting, and they show that their algorithm is quite robust to this addition of delay. And that's it for that lesson, so don't hesitate to send me an email if you have questions, and thank you for listening.